Pigeon. Instant messaging is a vital part of our daily lives. Given the sensitive information shared through these platforms, they are prime targets for cyber attacks. End-to-end encryption combats this by securing messages on top of TLS, so the only people that can read it are the sender and recipient, not any servers or intermediaries. And so what Pigeon is a end-to-end encrypted messaging platform. The functional requirements are you should be able to send messages between two clients on different hosts through the server. The end-to-end encryption of all messages such that the server and any intermediaries cannot view plain text messages. We used RSA for this. You should be able to register as a Pigeon user and have a unique identification. You should be able to add another Pigeon user, and you should also be able to be added as another Pigeon user. You should also be able to view contacts, view your friends, and view a chat history. So this will be the functional demonstration for Pigeon. So right now I just have the terminal open and the server is running in the background. So this demonstration is just going to be me and Anshul, and we're going to be messaging each other over different networks because we're in different houses, different hosts. So to start off, we're going to run the client. So we're just running with poetry. From there, we'll be prompted with some options, and the client's going to boot up. So some of the options are just options, which will tell us what we can do with this client here. Another thing we can do is list, which will say list the Pigeon contacts. Since I just booted the client up, I have no contacts. And to get contacts, I need to add someone. And then from there, I can select. So when I start the Pigeon client, I'll be assigned a ID here. So this ID is unique. And if I want to talk to somebody, I'll need to add them with that ID. So Anshul has booted up his client as well. And so I can get his ID and then just use it to add him. So there we go. I've invited him to be a friend.
So now that
Okay.
Abdul has sent me an invitation, I accepted it, and now I'll be sending him a message. So to do that,
Yep.
I quickly select uh, like this particular ID.
Are you sharing screen?
Yeah, I'm sharing screen right now.
Okay, cool.
So once I select, now I'm messaging Abdul. So let me send him a message saying, "Hello, friend," because he's a good friend of mine. And now Abdul should be able to
Yep, I'll
receive
share
my
my
message.
screen.
Yeah.
And so from there you can see, so I selected Anshul as a contact, and then now his messages come through with the timestamp, hello friend. And as you can see, it's very late in the morning, or
Yeah.
early. So yep, I can message him as well. I can say, cool. And yeah, then he'll get that as well. Maybe we'll just do one last demo here.
Yep.
So yeah.
I've received the message. Cool. It's 2 in the morning, which is fun.
Pigeon software messaging system's core feature is the encryption between client messages. This is to ensure that no outside parties are snooping in on the conversations between users. Now, right now, we have two devices set up with a client on each device, and we'll be sending some messages between them to demonstrate how the encryption software works. Right now, we'll be disabling it, however, to see how other people on the network might be able to see it. One of the tools we'll be using is Wireshark. Now, Wireshark captures all these packets on a given network, and you can analyze each of these packets, and you can see some interesting details. Oops. Such as here, you can kind of see some interesting details for its various packets. And we're more interested in HTTP packets, though. Now, currently, each client is constantly sending out some requests to see if they have gotten any contact requests. And we're just going to send one out right now. Uh, Boom. And we can see here, this is the push request, which is that we are requesting to add this person as a friend. And within here, we can see the JSON and we can see details such as the public key and such. Yeah, so with them added as a contact, by selecting them as a contact, we can start messaging. Now with the encryption disabled, sending a message such as hello from unsafe client, we can analyze this packet on Wireshark and we can see the interesting details. We can see who it's to, who it's from, date and time, and most importantly, the message. We can see the message is hello from unsafe client, and so can anyone else on this network. Now this isn't too good, and we'll be putting in our encryption right now to ensure that these messages can't be snooped in on. and bling, by just selecting the same contact again. Now, when we send a message, hello, this message is encrypted. We can see this post request here. This is the message that we sent out to the other client. And we can see all the typical details such as who's to, who's from, date and time. However, when we get to the message, we can see that's a lot more jumbled up and harder to understand now. This is the encryption hashing and makes it very hard for anyone to understand what the original message was.
Non-functional requirements and non-functional requirements were availability, reliability, security, and scalability.
Macron plays a crucial role in helping Pigeon achieve its security ASR by ensuring the integrity of the software supply chain. As the software supply chain attacks are becoming more prevalent and sophisticated, it's essential to have strong guarantees that the third-party code that we rely on is indeed what we expect. Macron does this by analyzing the software repository to determine its SALSA, which is supply chain levels for software artifacts levels. This analysis basically provides transparency about the build process and ensures that the dependencies in the artifacts meet a high security standard. By automating the checks, as you can see in this comprehensive report, and defining concrete rules based on high-level SALSA requirements, Macron can efficiently identify potential vulnerabilities or tampering in the build process. This means that any third-party code used in Pigeon is scrutinized to prevent credential theft, code tampering, or other malicious activities, thus safeguarding the application security. Looking ahead, as Pigeon becomes more complex, Macron can continue to enhance security by adapting its customizable checker platform to include new and evolving security requirements. This adaptability ensures that as the Pigeon's architectures and dependencies grow, the integrity and security of its supply chain remains robust. Regularly updating and extending Macron's checks will allow Pigeon to maintain its high security standards, meeting the evolving threats in the software ecosystem. As you can see in this particular report, we are currently only passing the first two SALSA levels, which is the script build and the version control. However, as this becomes more complex, we aim on making sure that the SALSA levels are meeting all the way to level 3, which will safeguard the entire CI/CD pipeline process.
So for security, we ensured security with unit tests. So what these unit tests did was they would just test the underlying encryption mechanisms and then also the encryption mechanism over descending high-level commands there. So we ran these unit tests to ensure security. On top of that, we had integration tests. And so these integration tests were run on the client while the server was still up. And so that's another way we were just ensuring that we were always meeting our security goals and everything was encrypted. And so these are more integration tests. So for reliability, one way that we tested and ensured that we were meeting our reliability requirement was that we created a GitHub Actions workflow that would always run the unit tests on the client every time there was a new push. So this would ensure that no matter what changes were made, we would always reliably be delivering the security requirements. Another way that we tested reliability and ensured reliability was with K6 tests. So when we were running a total of, as you can see, 25,000 virtual user transactions, we were able to ensure that we had about 98% accuracy with reliable transfers there. So that's reliability in communication. Additionally, we ensured reliability by having a min capacity of 2 servers in an auto-scaling target group. So what that means is no matter what happens, there's always going to be 2 servers running. So if one goes down, there'll be one as a backup. Here's an example of that. So this is a snapshot of the AWS console. And as you can see, 2 of the servers have gone down just due to them being overwhelmed. But the AWS auto-scaling policy is automatically just scaling up 3 more just to meet the demand. So for scalability, just coming back from that auto-scaling policy, so that's how we ensured scalability. We just had an auto-scaling group that would scale up based on CPU percentage or CPU utilization. So this is kind of a demonstration. So beforehand, when CPU utilization is low, just when the server's booted up, we'll just have 2 servers running by default. And as you can see here, CPU utilization is very low. From there, we run these K6 tests. And so what these K6 tests do is basically, it's just sending a message and then pulling that message back after 1 second of sleep there. So it's basically just a single one-way interaction, standard interaction. So here we go. So this is the K6 test being run, and in total is about 25,000 transactions. And so during this test, you can see the CPU utilization increasing. So this is due to the increase in number of virtual users, and correspondingly, the number of tasks is increasing. So it's scaled up to 5 to handle that demand. So after that, as you can see in the graph, after it's scaled up and the K6 load test is over, it can scale back down so that you're not wasting resources. And so the total tasks running are 2. So the last non-functional requirement was availability. And so we are basically leveraging AWS with their availability. So the server's running on AWS. So as long as we have credits running with that AWS account, the server should still be up and running. And AWS promises kind of 5.9 uptime. And so we're hoping that we can leverage that as well.
Okay, now I'll be exploring the C4 architectural diagram to Pigeon, our end-to-end encrypted instant messenger application. Coming to the context diagram, we have the Pigeon client, we have the context right? So we have Pigeon user. At the heart of our system are the users who interact with Pigeon client application. They can send and receive messages securely. And with the Pigeon server, it is the central server that routes encrypted messages between clients, ensuring that only intended recipients can decrypt and read the messages. The external systems, well, these are the servers interact with the cloud services like AWS for deployment and database management. These services ensure scalability, reliability, and security. Coming to the container diagrams, Pigeon client. We have two containers here, application container. This is where the main functionality resides. It's responsible for sending, receiving, encrypting, and decrypting messages. It's developed in Python and deployed in a Docker container. The SQLite database, this is the local database which stores the user data, including contact information, message histories, and encryption keys. It ensures that the user data is available offline and synchronizes with the server when connected. Coming to the Pigeon server container diagram, we have the Pigeon server application, which handles the sending and receiving of messages between clients. Then we have the Pigeon server database, which stores all the encrypted messages and chat invites until they are pushed. And we have the Pigeon server application basically interacting with the cloud provider to define the infrastructure. Coming to the component diagrams, let's have a more granular look into the architecture. This is the Pigeon client component diagram. So in this, we have the CLI front end. This is the command line interface through which users can interact with the application. Then we have the logical code. This manages the networking, encryption, and data persistence. It acts as the brain of the client, coordinating various tasks. Then we have the encryption manager, which handles the encryption and decryption operations using robust encryption algorithms like RSA. Coming to the network manager, this basically manages the communication with the server, ensuring messages are sent and received securely. Coming to the Pigeon server, we have the Terraform scripting, which basically defines the infrastructure for the Pigeon server, and the other two main components, which are the routing logic and model. So what the routing logic does is basically manages all the endpoint requests that are being received from the Pigeon client and basically routes them to receive or store all the data into the model component, which is basically the data structure for the Pigeon server. Coming to the component diagram for cloud provider, we have a very comprehensive list of components. So in this, as you can see, the Pigeon server basically pushes or pulls images from the ECR repository, which stores the Docker image. This basically stores the image in the ECS cluster, which basically manages the ECS services. The ECS cluster then in turn runs all the tasks that are defined by the ECS task definition. And the ECS task definition basically defines all the tasks that are being run in the ECS service. So the ECS service is responsible for running and managing all the ECS tasks. And you have the load balancer basically distributing all the traffic to the ECS server. Then you have the auto scaling component, which basically adjusts the number of ECS tasks based on the CPU utilization. And then you have the database and the security group. The database is basically Postgre, like the Postgre instance, which is basically managed by the RDS. And the security groups, well, they are responsible for controlling the inbound and outbound traffic between these clusters. So yeah, this is the overview of the architecture.
So onto the reflection. We used a monolithic architecture for both the client and server, which was more difficult to handle than anticipated due to the high coupling between internal components. Additionally, we do not have any defined bounds to logically separate internal components. So this tight coupling caused inefficiencies as team members had to wait for others to complete their code before proceeding with their own tasks. In future, we would address this by modularizing the internal components more effectively. This approach would reduce dependencies between components, allowing team members to work more independently and improving overall productivity. Designing the architecture for the application initially proved challenging because we did not fully understand the technologies that made it possible, such as the encryption techniques, the client-side API interactions. To address this, we developed architecture diagrams early in the process. This proved to be a good decision, as in making the diagrams early in the development, we understood how and where the new technologies like end-to-end encryption should be applied and what it needed to interact with. Automating integration testing was another hurdle we faced. Initially, we explored creating a GitHub Actions workflow similar to our existing unit testing suite. However, the complexity of managing the AWS environment and Docker containers led us to choose some manual testing options to demonstrate our integrated functionality. So like unit tests and then like a testing plan. Or not unit tests, sorry, not automated GitHub tests. So from this, we discovered that establishing a continuous integration pipeline in the beginning would have allowed us to verify and test our code regularly, more efficiently, and would overall increase our productivity and overall just reduce the likelihood of errors. So in future projects, we would prioritize setting up automated testing like CI pipelines to enhance our development workflow and ensure higher quality code. So developing the software system within a month posed a significant challenge since the team had assignments from other courses and this had many deliverables itself. So I would say the way that we ended up making time management a positive was that our team as a whole had a pretty collaborative spirit and effectively communicated through Discord servers, allowing us to overcome these constraints. So we used regular meetings, the intelligent division of tasks, and realistic deadlines to help us stay on track and deliver an MVP despite the tight schedule. In future projects, we would continue to leverage these strategies, ensuring that time management remains a strength even under demanding circumstances.